Hi everyone, in this video we're going to continue our discussion of techniques for computing limits, and we're going to do a lot of examples on finding limits. So this is part 2 of the techniques for computing limits videos. So we're going to start with this couple of rules. So when you have polynomial functions and rational functions, the polynomial functions, the limit as x goes to a of a polynomial function is just the function value at a. And that's because there are no gaps. This isn't a piecewise function. The domain of a polynomial is all real numbers. So the limit as x approaches a value is just going to be the function value. So for example, here, as x goes to -2, and as I was saying in the previous video, anytime you encounter a limit, plug it in, see if it is the function value already. So when I plug in -2 into my function, right, this is my polynomial function, let's call it p of x, then I'm going to have -2 cubed minus 5 times -2 plus 1, and -2 to the third, that's -8 minus, oops, that's a minus there, minus is a minus is plus, so plus 10, and then plus 1. So, and remember, always do your order of operations from left to right. So -8 plus 10 is 2, so 2 plus 1 is 3. And so that will be it. That's my limit. So for polynomials, just plug in the value and you'll get your limit. Let's try another example. We'll take this rational function. So the limit as x goes to 4 of x plus 1 over x minus 2. So for rational functions, the limit as x goes to a of the quotient of two functions is the quotient evaluated at the a value, provided the g of a is not 0. So for this function, as x goes to 4, let's see what happens. Let's just plug it in. So we're going to plug in x equals 4 and see what happens. So I'm going to have the limit as x goes to 4 of 4 plus 1 over 4 minus 2. So I just get 5 over 4 minus 2 is 2, 5 halves, and I'm done. So with limits, if you plug it in and you get a number, you're done. That is the limit. So I can say, therefore, the limit as x goes to 4 of x plus 1 over x minus 4 is 5 halves. Leave it in fraction form. There's no reason to change that to 2.5. I prefer fractions. All right, so let's try another example. What happens when the quotient is 0? So let's look at the example that I had written for at the end of the last video of part 1. All right, so when we have this limit, evaluate the limit as x goes to 2 of x squared minus 4 over x minus 2. Again, I see a limit, I'm going to plug it in. So I'm going to plug in x equals 2, right? The value that my x is approaching. So I'm going to have the limit as x goes to 2 of 2 squared minus 4 over 2 minus 2. And notice that now I have 0 over 0, which is, up until this point, you've been told that this is undefined, but now we're in calculus. So this is not undefined. This has a limit. We need to find it. And so we're going to do some algebra. So when you get 0 over 0, this means do some algebra. So what is the algebra that we are going to do? So I'm going to take my limit and I'm going to try to figure out, okay, what kind of algebra can I do with this function? X squared minus 4 over x minus 2. Notice that I can factor the numerator. So when I say do some algebra, that you're going to analyze the function that you're given and see what can you do. In this case is factor. If you have a radical, rationalize. If you have fractions, like fractions within a fraction, get a common denominator. So what are the algebra steps that you can do to simplify that function? So that's what you're going to be looking for when it says do some algebra. What algebraic steps can you take to simplify that? So I'm going to have the limit as x goes to 2, x squared minus 4, that's a difference of squares, so that factors into x minus 2, x plus 2 over x minus 2. And so notice here that I can simplify. how can I simplify? I have x minus 2 divided by x minus 2, so I can reduce those. X minus 2 divided by x minus 2 is 1, so I'm left with the limit as x goes to 2 of just x plus 2. And now can I plug in 2 again? Let's see what happens when I plug in 2. I'm going to have 2 plus 2, which is 4. So now that is my limit. So therefore, I can say the limit as x goes to 2 of x squared minus 4 over x minus 2 is 4. What does this mean? Remember in the prior videos about the definition of limit, we talked about the limit is telling you a statement or asking you a question. What value are the y values approaching as x gets close to 2? So what we just found out is that the y values are getting close to 4, the y value of 4, as the x values approach 2. And if you go back to the original, right, looking at the function, right, saying that f of x is x squared minus 4 over x minus 2, I'm going to ask you, what is the domain of this function? We have a denominator, so what do you know about denominators? Denominators can't be 0, right? So then x minus 2 can't be 0, which that implies that x can't be 2, which is why we're interested in, okay, so x can't be 2, that's not in the domain, but everything else is in the domain, right? The domain of this function is minus infinity to 2, not including 2, union 2 to infinity. So there are y values for all of these numbers, and so except at 2. So we're asking, okay, what are the y values doing near x equals 2? Because clearly, up until 2, to the left of 2, right, you have y values. To the right of 2, those x values have y values. So our question is, what are those y values doing? And so this limit is telling us they're close to 4. So let's look at the graph of this function. All right, so here's the graph of the function. So notice that as x approaches 2, right, this is our function. What are the y values doing? So as x goes to 2 from either side, the y values are getting close to 4. Now there is no y value at 4 because x equals 2 is not in the domain. So we don't have a y value there. But the y values are getting close to 4. So this translates to meaning we have a hole in the graph, and you can see it there. And algebraically, you can tell when there's a hole in the graph when you have a term that cancels. So like in this case, right, when we had simplified this, as soon as I see that, oh, I'm going to cancel those, this translates to a hole in the graph of the function. As soon as you cancel off a term, that translates to a hole in the graph. Where is the hole? The hole is going to be at the x value, so x equals 2, and the limit, right? The y value that should be there, but it isn't. So at 2, 4 is where the hole is. Let's try another example. All right, so let's look at this example. So I have evaluate the limit as x goes to negative 1 of x cubed plus 1 over x plus 1. And I have a limit, so evaluate it when x equals 1. So plug in, or negative 1, sorry. Plug in x equals negative 1. If you get a number, great, you're done, right? That's your limit. And so what happens when I plug it in? So limit as x goes to negative 1. So I'm going to have negative 1 cubed plus 1. You can probably already see it without really doing much work. Negative 1 cubed is negative 1, so I'm going to have 0 over 0. Now, 0 over 0, what does this mean? This means this does not mean I'm defined anymore, right? This means do some algebra. So I'm going to try to ingrain that in you. Do some algebra. As soon as you see 0 over 0, do some algebra. Now, explore the function. What does it mean to do some algebra in that function? What can you do? So limit as x goes to -1 of x cubed plus 1 over x plus 1. All right, what kind of algebra can I do? Well, x cubed plus 1 looks like a sum of cubes, so I can factor. So factor using the a cubed plus b cubed formulas. If we remember those, if we don't, that's okay, we'll review them. So this factors into a plus b, and then a squared minus ab plus b squared. And just to review the difference in case you encounter it elsewhere, that's a minus b, right? And a squared minus or plus ab, and then minus b squared. So those are your sum and difference of cubes formulas. And so here I can use the sum of cubes. So I can say it's kind of like my a is x and my b is 1, right? A cubed plus b cubed, x cubed plus 1 cubed, which is 1. So I can then do some algebra here by factoring. So I'm going to factor and say this is the limit as x goes to -1 of factor x cubed plus 1. So this is going to factor into x plus 1, right? A plus b, so x plus 1, times a squared, so x squared, minus ab, so x times 1 is just x, and then plus b squared. 1 squared is just 1, all over x plus 1. And now notice that what did that factoring do for us? I can simplify, produce. X plus 1 divided by x plus 1 is 1, right? Those divide out to give us 1. So I'm left with the limit as x goes to -1 of just x squared minus x plus 1. And now plug in again and see if we get a number. I don't know what I said to check. To see if you get a number. So plug in x equals -1, because remember with limits, if you get a number, you're done. So plug it in. So I'm going to have -1 squared minus -1 plus 1. So what does that give me? -1 squared is positive 1 plus 1 plus 1. So I'm going to get 3. So what does this mean? Now, as in the previous example, I said as soon as you're able to cancel out a term like this, that means that there's a hole in the graph. And where is the hole? So let's summarize it here. Since I have the limit, I'm looking for the limit as x goes to -1 of x cubed plus 1 over x plus 1, right? So that means that my function is x cubed plus 1 over x plus 1. And again, I'm going to ask you, what is the domain of this function? X can't be, the denominator can't be 0, right? So that means that x can't be -1. I wonder if that's why we're finding the limit as x goes to -1. That is exactly why, because -1 is the only x value that is not included in the domain. So that means that I have a graph for everything up until -1, and then not at -1, and then from -1 all the way to the right, all the way to infinity. There are y values there. So what we're trying to see then is like, okay, so x equals -1 is not in the domain. So there's no specific y value, but I have a graph on either side of that. I have y values. So what are those y values doing? So that's what this limit is asking. What are those y values doing? So now I know based on my limit that the y values approach 3 as x approaches -1. So that means, and because we have a hole, that means that the hole is at -1, 3. And notice that when you factor this function, right, when we factored it, let me do it over here. I have f of x is x cubed plus 1 over x plus 1. We factor that. I'm just going to repeat my steps from above. Okay, so the reason that I'm doing this is as soon as we cancel this term, that means that there is a hole in the graph. But most importantly, that means that this function, the graph of f of x equals x cubed plus 1 over x plus 1 looks like the graph of y equals x squared minus x plus 1, the leftover. After we cancel that term, what's left over? So it looks like that, except with the hole. Right, there is a hole in the graph at -1, 3. So let's look at the graph real quick. I'm going to put it over here. So here's my graph for this function. And so there is a hole at -1, 3. Right, so that means, so this is my, this is the graph of y equals x squared minus x plus 1. So that's what I mean by looks like. So when you're able to cancel off a term, right, that means that what's left over, that's what your graph looks like, but we retain the domain of the original function. This function, my f of x, the domain does not include -1. So the domain is -infinity to -1, union -1 to infinity. So my graph reflects that. So the graph looks like that quadratic, but we retain the domain of our original function. X cannot be -1, right? -1 is not in the domain of f of x. So hopefully that is making sense. This is a pretty tough concept sometimes to grasp in calculus, the idea of the limit. I like to use graphs to show you what the limit means. So when we say that the limit as x goes to -1 of our function and that this equals 3, that means as x approaches -1, the y value is approaching 3. It doesn't equal 3, right? The function value doesn't equal 3 because notice this -1 isn't even in the domain, so there's no y value there. But the limit is just allows us to find what are the y values doing? What are we approaching? What are we near? Okay, so in the next video, I don't want my videos to get too terribly long, but in the next video, we're going to do a couple of examples like this. So a little more complex, a little more in-depth, and a little more algebra to do. So on part 3 of techniques for computing limits, I'm going to do these 2 examples.